How do we keep 1.5 degrees C alive? Well, we have to make every building count. There's an old saying in the US, if you don't know where you're going, you'll end up someplace else. So where do we need to be? What are the targets we need to hit? This year, the IPCC came out with a report, Climate Change 2021. And in that report, they laid out the carbon budgets for meeting the 1.5 degrees C, for having a decent probability of meeting 1.5 degrees C. And the carbon budget for doing that is roughly between 300 and 400 gigatons of CO2 total. That's our total carbon budget in order to have a good probability of meeting the 1.5. So what does that mean? Well, today we emit about 40 gigatons of CO2 a year globally. And we hear a lot of talk about phasing out CO2 emissions by the year 2050. If we draw a straight line down from what we're emitting today all the way to 2050, that's 600 gigatons. That's less than a 50% probability to stay within the 1.5 degrees C or to meet that target. So that in essence doesn't work. Well, most scientists are calling for a 50% CO2 emissions reductions by 2030. If we follow that line down, if we meet that target and we follow that line down, then we phase out CO2 emissions by 2040. That gives us a 67% chance of meeting the 1.5. That's a good probability. And we think the building sector, our sector, can do even better. We can reach a 65% reduction by 2030 and phase out all emissions in the building sector by the year 2040. So a 50 to 65% reduction by 2030 works, and then a phase out by 2040. So that's our carbon budget. This is the way we visualize, and the International Energy Agency visualizes, CO2 emissions by sector. You can see that building operations is 27%, industry 43%, and transportation 23%. So we're responsible for building operations, which is 27%. But if we look at industry and tease out what we're responsible for, building materials and construction add another 10% of global emissions. That's cement, steel, bricks, glass, and everything else to build a building. And then all the other construction that's associated with buildings, like site work and infrastructure, that accounts for another 10% of total CO2 emissions globally. So roughly, we're responsible, in a sense, for almost half of all total global emissions. So how do we achieve a zero carbon built environment? That's buildings and the infrastructure that goes along with it. Well, it's a two-step process. Step one is planning, design, and construction. It's what we do. And there we call for electrification, no on-site fossil fuels. Step two is adding the renewables. If we do those two things, we get through planning and design 70 to 80% of the way there. And then step two, we add the renewables, we can get to zero carbon. So how do we do that? Well, if we plan correctly, for example, establish growth boundaries, so we're not increasing the infrastructure, infill, use public transportation, bring urban agriculture, bring agriculture in back into the city, design buildings using passive heating, cooling, and daylighting systems, and then using the appropriate materials, reducing the embodied carbon of materials, and even using carbon sequestering materials, we can get 70 to 80% of the way there just through strategies, design strategies, no cost or low cost options and strategies that we have. And then step two, we then need to power the rest of the building's needs with renewables, and that's on-site renewables or to bring in electricity, for example, from offsite locations that are powered by renewables. So that's how we get to a zero carbon built environment. So how do we actually do it? Well, there are 3 steps to doing it. Step A, design to the latest building code standard or better. Why? Well, first of all, we have zero carbon building code standards that get us very, very low carbon operating energy. ASHRAE 90.1 2019 is an excellent code. The IECC 2021. China has a nearly zero energy buildings code, plus on-site and off-site renewables. Many European countries now are required to get to nearly zero energy plus on-site and off-site renewables. So we have the standards out there. We have international standards. And if we just design to the latest code standard, then we get a very efficient building. There is nothing stopping us from designing an efficient building. If we have a lesser code standard that's not the latest, that's only a minimum standard. So we can still design to the latest code standards. And this is to illustrate what that does. This is the energy consumption of a building in around the year 2000. This is how much in different climate zones, 100,000 square foot office building used. If we design that building today to the latest code standard, this is how much energy that building would use. Very, very little. And half of that energy is the plug load. So the part that the code addresses is a very, very small portion. So we can easily then address the building's energy consumption because it's very low with renewables. So the first thing is design an energy efficient building using at least the latest code standards. And then we can do all sorts of things also to even reduce it more. We can look at the envelopes, make it even more efficient, daylighting strategies, all the passive heating and cooling and ventilating strategies that we know that are design options that don't cost anything can also bring the efficiency of the building way up and the building's energy consumption way, way down. So the second thing we need to do is design all electric, plus renewables, no on-site fossil fuels. So we design all electric, we address the remaining building's energy needs after we've designed an efficient building with either on-site renewable energy when we can do it, or we bring in energy off-site but from renewables. We insist on renewables. That gives us a zero carbon building. What about all the existing buildings out there? Well, the formula is the same. When we renovate them during renovation cycles, we can make them more efficient, get rid of the on-site fossil fuels, electrify them, and then bring in on-site or off-site renewable energy. And we discovered something really interesting. This is New York City, an aerial view of New York City, and you can see in those red circles, that's where all the big, big buildings are in New York. Over 50,000, 100,000 square foot buildings are in Midtown Manhattan, downtown Brooklyn, downtown Manhattan. So in those small circles, that's only 2% of all the buildings in all of New York City. It's a very small number of buildings. That small number of buildings are responsible for 48% of all building sector, building operations emissions. It's huge. So a very small number of buildings are responsible for a huge portion of the city's building sector emissions. We can see the same thing in Chicago along the waterfront, very, very big, big, big buildings, and then miles and miles of small buildings. Same thing in Philadelphia, same thing in Guangzhou, same thing in Istanbul, Turkey, and downtown areas, some huge buildings, and then lots and lots of smaller buildings. You can see the same thing in Nagasaki, Japan, along the waterfront, huge buildings. And then in back of it, miles and miles of small buildings. Same thing in Sydney, Australia. So based on that, we can develop a two-tier strategy, two-part strategy. First, with the big building emitters, there are very few of them in each city. There aren't that many, and they're responsible for almost half of all emissions. So we work our way down from the biggest buildings till we get to half of emissions. It'll be a relative handful of buildings, and we require them to get to zero carbon by the year 2030. And we provide incentives for them to do it. They'll usually hit a capital improvement cycle, and so it'll be really inexpensive to get rid of on-site fossil fuels, electrify, and then use on-site and off-site renewables. And we can give them low interest loans, tax advantages. There's all sorts of things cities and local governments can do. And then we require all the rest of the buildings to get to zero carbon by 2040. We give them more time. These are the smaller buildings. And we look for times when they're going to actually undergo a renovation. So getting to zero is not that difficult and doesn't cost very much. At point of sale, a zoning or use change, when they undergo a renovation, when they're replacing equipment, replace it with more efficient and electrify and get rid of on-site fossil fuels, and give them the same incentives to do that. If we do that, we can transform the entire building sector, existing building sector, to get to zero carbon by the year 2040. And then last but not least is we have to zero out embodied carbon. All the materials and construction that goes on in the building sector, and there are literally hundreds of thousands of materials that we can choose from. So how do we zero out all that? Well, we discovered something interesting. Here's the way we usually see now global emissions. And if we reconfigure the industrial sector, we see that just two materials, concrete and steel, are responsible for almost half of all emissions in the industrial sector. And most of that concrete and steel and emissions come from building buildings and all the infrastructure that goes along with buildings, the roads, the site work, the parking lots, the bridges, all of that is the concrete and steel is attributed to the built environment. So just two materials are responsible for half of all industrial emissions. And if you throw in aluminum, it's over 50%. That's kind of like the big buildings, small buildings. You have two materials and then hundreds and millions of other materials and products. And you can see in a building, it's the structure, the concrete and steel and structure that makes up 50, 60, as much as 75% of the total emissions of building the buildings. And you can see if you renovate a building, you then don't have to build all that new structure. Keeping existing buildings and renovating them and reusing them is really the greenest building. It's the one you don't have to build. That's already been built. So now what? How do we, again, get a handle on steel and concrete and then all these other materials? Well, the first thing is we have to change the conversation. Well, and that conversation has been changing. And recently we discovered that steel and concrete was responsible for this huge amount of emissions, and then followed by aluminum and glass. And we're starting to see that now in mainstream media. Concrete, the most destructive material on the planet, from The Guardian and Bloomberg. Steelmakers next in the crosshairs as climate pressure grows. And there's an alternative, mass timber. We can use mass timber, cross-laminated timber, glue-laminated timber. We're starting to see now crossing glue-laminated bamboo in the global south being discussed. This gives steel and concrete competition. So it incentivizes steel and concrete to change and become low carbon. So what can we do in the design, planning, and architecture professions? We can look to reuse when we can, reduce and sequester carbon. Let's look at reuse. Like I said, the greenest building, development, or neighborhood is the one that's already built. So if we can repurpose and upgrade urban areas, that's better than tearing them down and building new. When we can do that, we can also renovate existing buildings, adaptive reuse. We'll see a lot of that because of COVID, and use local or recycled materials. And if we do design new buildings, then we can design them to deconstruct them later on after their usable life, to reuse materials. That's becoming now an option within the architecture profession. The second thing we can do is reduce by, again, establishing growth boundaries, infill. There's usually a tremendous amount of area that can be infilled and densify. We know that that's not a COVID spreader, by the way, it's overcrowding. So we can infill and save all that infrastructure. We can optimize structure. We usually over design now anyway. And then we can specify low carbon materials. We're calling for an immediate 30 to 40% reduction in our specifications when we specify materials, and then a 50% reduction by 2030, zero by 2040. But we should get concrete and steel to zero carbon as quickly as possible, preferably by 2030. And we're beginning to see public policy now come into play with that. And the last thing we can do is sequester carbon, use from sustainably managed forests, sustainable and glue laminated wood, and possibly bamboo. We're beginning to see the concrete industry and steel industry change. There's carbon positive aggregate now for concrete, injecting CO2 into concrete, changing CO2's properties. So we reduce the amount of CO2. Going to electric arc furnaces and renewable energy for making steel with recycled steel, using biomaterials with renewable energy to actually make the materials, and then sequestering carbon in landscapes and soil and site work, and bring agriculture into urban areas. Also can sequester a huge amount of carbon and reduce transportation. So how fast can we make this change? We have to make this change, really in the next 18 to 20 years. Well, let's look historically how change is made in our sector. This is the Flatiron Building in 1891. You can see this is how it's changed today. The change is dramatic. We've gone from low-rise buildings, all bearing wall construction, small spaces, small windows, to huge high-rise buildings that are all glass. So how did we make this change? Well, the first modern building, considered the first modern building, was in Germany. It was called the Bauhaus. And here you can see structure moves inside the building, point loads rather than masonry bearing walls. So you could open up the floor plan. And then you could hang the exterior wall, it didn't have to be masonry anymore, or load bearing. You could hang it from the structure and bring in lots of light, daylight, and natural ventilation. So this is considered the first modern building. That was in 1925. What was going on back then? Well, you can see things were pretty primitive in 1925. We had radio vision, we didn't have television. We had the first Model T truck, for example. You couldn't make calls overseas. We didn't have cell phones, obviously. It wasn't until 1927. So things were pretty primitive back in 1925. Well, in 1928, conditions were really bad. The architects, the leading architects and planners and designers got together and held the first international Congress of Modern Architecture. And they were responding to terrible conditions in Europe during the beginnings of the Industrial Revolution. Housing was in the industrial areas, and pollution from burning coal, for example, was terrible. People were dying early, and The architects and planners and designers got together and set out guiding principles to get housing out of the industrial areas. They called for function-based zones and high-rise housing blocks and abundant sunlight, solar exposure for all housing units, putting the housing units in parkland, things like that. So they set out these utopian principles and for this, essentially for environmental reform. And Le Corbusier then set out the 5 principles for a modern architecture: column wall separation, get rid of the bearing walls, for example, or free up the facade so that you can open it up and open up windows to the outside. The horizontal window, free up the design of the plan so we can have flexible space. And he called for roof gardens, actually replacing the vegetation we took by building the buildings and putting it back up on the roof. Interesting. So all that happened in 1928, 29. By 1932, that European movement of modern architecture came to the U.S. in an exhibit called the International Style. And the reason being, you could take that building type, that modern building, and put it anywhere in the world because we have fossil fuels, they were cheap. You can climate control any space. So by 1939, you could see the beautiful Johnson Wax building, big open floor space with column loads. By 1949, you had the all glass house in a very, very cold climate, a single glass, all glass house in a cold climate in Connecticut, New Canaan, Connecticut, the Philip Johnson Glass House. It was demonstrating that essentially we can build all glass and climate control the building to where it was comfortable because we had fossil fuels and cheap fossil fuels. By 52, you had single glass high-rise buildings throughout the world. So here's the beautiful Lever House. And then by 56, you had entire new cities planned on the modern principles. So how long did it take to go from the Bauhaus to the Lever House? From 1925 to 1952 was 27 years. We changed the world in 27 years with these primitive tools that we had, T-square and triangle. It took years to do a set of construction documents. We had to dip a pen in an inkwell in order to draw, and we didn't have erasers to erase the ink. We had to scrape it off a drawing with a razor blade. This is how we changed the world in 27 years. You couldn't do a curve because you couldn't dimension it. So you had French curves, but you couldn't dimension it and put it in 3 dimensions. So everything was rectangular. Every building in the world during that period pretty much was rectangular. It wasn't until 1960 that we actually got a pen to draw with and a rapidograph. And the first laptop didn't come in until 1991. So we changed the world in 27 years with these primitive design tools. We have 20 years now, roughly, from 2020 to 2040 to meet the 1.5 degrees C target to phase out all emissions. So at COP26 in Glasgow, we called for a 50 to 65% reduction for our sector and all sectors, at least a 50% by 2030. If we meet that, we will be on a path to zero out CO2 emissions by 2040. And organizations, all the major organizations came together along these lines, calling for the 50 to 65% reduction by 2030, zero by 2040. These are all the design professional organizations and planning organizations representing over 1 million design professionals came together and aligned along these targets and are now working so that our professions meet these targets, so that the building sector and the built environment meets these targets. And 60 to 70 of the largest firms in the world, responsible for over 300 billion in annual construction, has also signed on to what we call the COP26 communique to meet these targets, and will work within their firms to do the same. So what does that all mean, and what is our flow chart for the next 20 years look like? Well, we issued the communique in Glasgow this year, and we called for all new buildings to be zero carbon operations and to at least design to the latest code standards. By 2025, we call for a 50% embodied carbon reduction in steel and concrete. And by 2030, zero carbon steel and concrete. All other materials, then a 50% reduction we're calling for by 2030 in embodied carbon. And by 2030, we should have all big buildings, those responsible for roughly half of a city's building sector's emissions, at zero carbon building operations, electrify them, and bring in on-site or off-site renewables to operate them. So that by 2040, all buildings then built in 2040 will be zero embodied carbon, and will then renovate the remainder of the small buildings to zero carbon building operations. This is what the flow chart looks like to meet the 1.5. It is not that difficult. Why? Because look at the tools we have. We were using ink pens that we dipped in an inkwell to do drawings back to change the world in 27 years. We have now roughly 20 years, and these are the tools we have. We have simulation tools. We can look at daylighting strategies, passive heating and cooling strategies, solar. We can look at solar opportunities, and also solar energy is now the cheapest electricity in history. And that happened a year ago. It became cheaper than any other fuel source. So what's going on in the US and then globally? So in the US, in 2005, for example, from 2005 to 2020, obviously floor area increased. We keep building in the US. We added 53 billion square feet to our building sector. We increased our building sector stock by about almost 20% from 2005. But in 2005, something interesting happened. Prior to 2005, all the way to the beginning of the Industrial Revolution, when floor area went up, so did energy consumption in the building sector, and so did emissions, because everything was fossil fuels. Well, something happened in 2005. This is energy consumption in green. Energy consumption flattened out. It didn't go up. Even though we were building more buildings, we were bringing them in more efficient and then renovating, so that we actually did not increase any energy use in the building sector. We actually reduced it by 5.2%. But look at emissions. Emissions has gone down 30% in the building sector in the US, and that's due to cleaner fuels. That decoupling from actually building and then reducing emissions is unprecedented in US modern history. Never happened before. But we show not only can it be done, but it's saving consumers money. They're using less energy in a building if buildings are becoming more efficient, and we're going now to renewables. And this is what we project. We're now down 30% in the US. If we clean up the grid by 2035 and have incentives to electrify buildings, we should be at a 72% reduction by 2030 and zero out all emissions, building operations emissions, by 2040 in the US building sector. Well, what's happening globally? Well, floor areas increased from 2010, for example, to 2020, the last decade. Floor areas increased 22%. So we're obviously building globally and adding to the building stock of the world. This is energy consumption. Well, energy use went up, but not as much. Didn't increase as much, flattened out in 2018, and because of COVID, 2019 to 2020 actually dipped about 1%, dipped a bit. So it looks like energy consumption is now peaking and flattening out. But look at CO2 emissions. In 2018, 2019, all of a sudden, CO2 emissions has dropped dramatically. And why has that happened? Well, first, we're seeing a decoupling now. What has taken place in the US over the last 15 years is now beginning to take place globally, and that's good news. And why is that happening? Because in 2020, why did we see that huge drop? In 2020, renewable power was the only energy source for which demand increased while consumption of all other fuels declined, says the EIA, and they see that as being the new normal moving forward. That is good news. So we need to make every single building redesigned zero carbon from here on out. It is not that difficult to do. If we do that and we renovate the existing building stock and address our building materials, use alternatives, use carbon sequestering materials, we will keep 1.5 degrees C alive because we're responsible for almost half of all global greenhouse gas emissions. Thank you very much.